So in this video, we will be talking about vertical compression and also vertical stretches and how we can graph them. So here I have two questions, A and B, and then it says sketch and label f of x, 4 times f of x, -1/2 times f of x, and -5 times f of x. So let me just draw the axes. Let's do it this way. And then for the first question, I have f of x equals to square root x. So we know that f of x is square root of x. So we know that square root of x is basically like a quadratic function, except it is not reflected, but is rotated 90 degrees, because we know that x cannot be negative or else it will be imaginary. And so it always has to be positive. And if you're not sure how to graph this, you can always plot points. So I would recommend plotting or substituting x as a number that can be square rooted. So don't choose numbers like 3, because you can't really square root that. You can choose, for example, 4. You can choose 4. You can choose 9, 16, 25, and so on and so on. And the reason why I do this is because 4 can be square rooted. All of them can be square rooted. And so let's say I don't know how to graph this, and then I can say, okay, what if x is 4? Then that would be 2, because 2 times 2 is 4, or 2 squared is 4. And then here it would be 3, because 3 squared is because 3 squared is 9. And then square root of 16 would be 4, and then 25, it's 5. So I can kind of see the pattern here. When x is bigger, the y is actually smaller. And so I can say, okay, let's say, let me just graph the points here first, like that. So this is 2, this is 4, this is 6, 2, 4. Okay, so here it says when x is 4, y is 2. So when x is 4, y is 2. When x is 9, let's do it like that. This is 9. I can just plot it so it's easier. Okay, so when x is 9, y is 3. So it would be something like here. And then you can kind of see the pattern here. Oh well, it's not really good, but basically it looks kind of like a quadratic. It looks something like this, but that wouldn't be a function. Remember in the other video we talked about how a function can only have one y input for every x input. So it cannot have more than one y output for one x value. We cannot do that. And plus, as I said earlier, x cannot be a negative because it is a square root. So here we see there's different kinds of f of x. We see 4 times f of x. So what would that be? So we can try plotting it inside. So 4 times f of x would be 4 times square root x. So you can kind of imagine that it is more steep, because remember, when the number in front of the function is greater than 1, then we know that it is a vertical stretch. But if it's, for example, like 1/2, it is gonna be compressed. So let's try to focus on this one first. And so we know that since it is a positive, we know that it has the same direction as this, but it is more steeper. So it will look something like that. It's not perfect. Let me move this away so that I have, so that I have enough space. Oh no. Okay. Oh, it moves everything away. Let's just do this. And then I'm gonna erase that and put that here. Okay, so as I said earlier, it is greater than 1, so it's gonna be steeper, so it will look something like that. And then for this one, on the other hand, we see that it is less than 1, so we know that it is going to be compressed, so it looks something like this. But if you take a closer look at this function here, you see that there's a negative sign. When that happens, we know that it is flipped over the x-axis. And so what that means is that here, as we draw earlier here, this one would be flipped, so it would look something like this. Now I know that we said that since it's a square root, it cannot be negative, but we have the negative sign, so it doesn't matter if this cannot be negative. It has negative sign, so then we can flip it over. So it would look something like that, around like halfway of the regular function. And then finally we have -5 times f of x. Now 5 is greater than 1, so it will be a vertical stretch, and we can kind of see that it will be a bit more steep compared to 4. And then as you can see, it is a negative sign, so it will be negative, so it will look something like that. So here you have it, and I can just do it like that, so that's more clear. Because if I do it like that, it kind of looks like an exponential function, but it is not. So we need to be careful when graphing that. And then it says label, so we can just label it as this is f of x. This is 4 times f of x. Sorry, 4 f of x. And then this is -1/2 f of x. Oh, I always draw the bracket. And then -5 f of x. So there you have it. This is an example of how you can graph different kinds of version of one function based on the vertical stretch or compression. Now let's try to do another one. Here we see that it looks like a quadratic function, right? We have x squared, and then the b, it's in terms of standard form. And you notice that we don't have the c, and that probably just means that the y-intercept is 0. So how can we do that? Let's first start off by trying to see where the x-intercepts are. And remember, in order to find the x-intercept, we need to first factor it. So I can say, okay, well, I know that -x times x would be -x squared. And I want a positive number, so negative would become positive. And so this is how you factor it. So if you want to double check, you can always expand it, and you get -x squared plus 7x. So let's try to draw the axis again, like that, and like that. Is it straight? Oh well, never mind. So we know that the x-intercept is at 0 and 7, because when -x is equal to 0, that just means x is equal to 0, and when x minus 7 is equal to 0, that just means x is equal to 7. So we know that the regular one would be in blue, so let's just be clear on that, and also do this so that it's clear for everyone. Okay. So yeah, x is equal to 0, which is here. Let's draw the axes. So maybe like 1, 2, 3, 4, 5, 6, 7. So we look something like this. And then it's negative, so we know it's pointing downwards. And so we can kind of just briefly draw something like that. And oh, what happened? Uh-oh. Let's let's draw this again. So that's clear, that's purple, that's green, and then this is red. Now let's try doing the purple one. So 4 times f of x. Now again, same concept here. 4 is greater than 1, so we know that it is a vertical stretch. And so it will look something like that. You know what? Let's try drawing this less pointy, so that we have space. So yeah, we can say that this is like that. The scale is not important in this case, because we want to show the most important part is to show the transformation. And again, why is this disappearing? Did I click something? Yeah, maybe. Anyway, so 4 times f of x is vertical stretch, so it looks something like that. Let's draw it slowly. My hand is kind of shaky. Still not very used to this iPad. Yeah, it looks kind of like that. Apologies for my drawing. Now let's move on. -1/2, again, it's flipped over the x-axis, so it will instead point upwards, and it will be a vertical compression. So it will look something like that. Yeah. And then finally, -5 times f of x. Again, it's flipped over the x-axis, and it has a vertical stretch of -5. So it will be even steeper than the one in purple. So it will look something like that. Notice that they all have the same x-axis, because here we're just focusing on the stretch. And so when I label them, this would be 4 times f of x. The blue one is the original one. The green is -1/2 times f of x. And then the red is -5 f of x. So there you have it. This is how I graph and label the different versions of an original function. So this video mainly focuses on the vertical stretch and vertical compression. Remember, when the number in front of f of x is greater than 1, then we know that it is a vertical stretch. If it's less than 1, which for example, it could be, for example, 0.9, 0.8, 0.7, you get what I mean. It would be a vertical compression, and when you see the negative sign, it means that it is flipped over the x-axis. Thank you for watching. I'll see you next time.